July 1st, 2025, a robotic telescope in the Rio Hurtado Valley of Chile sweeps the night sky. Pixels shift, light bends, something moves wrong. Not slow like an asteroid, not curved like a comet bound to our sun. Straight, fast. 137,000 miles per hour when spotted, 420 million miles out, already inside Jupiter's orbit, but screaming from somewhere beyond our solar system. The third visitor from interstellar space we've ever caught, and this one breaks every rule. You've heard about Oumuamua in 2017, cigar-shaped, tumbling, gone before we knew what hit us. You know about 2I Borisov in 2019, classic comet, icy tail, nothing shocking, but 3I Atlas, different speed, different chemistry, different path. And here's the part that makes astronomers lean forward. On October 29th, 2025, when it reaches Perihelion, its closest point to the Sun, it stays 1.4 astronomical units out, 130 million miles, just inside Mars' orbit, never crossing Earth's path. Most comets dive close. This one keeps its distance. Why? What does that distance tell us about where it's been and what it's made of? If you value documented astronomical discovery and interstellar science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's official science pages published July 3rd and October 2nd, 2025, peer-reviewed data from the James Webb Space Telescope's NIR spec observations, published August 25th, SAT 2025 in preprint on AR Carx5, spectroscopic findings from the Very Large Telescope in Chile, reported by the European Southern Observatory on August 23rd. 2025 and orbital calculations from the Minor Planet Center's official designation records updated through October 3rd, 2025. These aren't press releases, these are observation logs, spectrograph readouts, and trajectory models published by research teams at UCLA, the Pontifical Catholic University of Chile, and the SETI Institute. Now back to the information. The ATLAS Survey Asteroid Terrestrial Impact Last Alert System runs 4 robotic telescopes, Hawaii, Chile, South Africa. They scan the entire visible sky every 24 hours, hunting near-Earth objects that might hit us. On July 1st, the Chilean site flagged object A11PL3Z, faint, moving. Follow-up observations rolled in from the Zwicky Transient Facility at Palomar Observatory in California. Pre-discovery images surfaced. The comet had been in the frame since June 14th. 2025 is now but too dim to trigger alerts. Orbital calculations started. Speed, 61 kilometers per second. Eccentricity, 6.141. Any orbit with eccentricity above 1 doesn't loop back. It's open-ended, hyperbolic. And 6.141 is the highest eccentricity ever measured for an interstellar object. More than 5 times Oumuamua's 1.2, nearly double Borisov's 3.4. This thing is moving on a trajectory so straight it barely curves around the Sun. July 2nd, 2025. SETI Institute hosts a live broadcast. Dr. Simon Steele, Deputy Director of the Carl Sagan Center, Dr. James Davenport from the University of Washington, Dr. Ariel Grakowski, SETI Postdoctoral Fellow, Dr. Wael Farah, CETI Chair and Allen Telescope, Array Project Scientist, they confirm it, Interstellar, the designation goes official, 3I Atlas, third interstellar object, the I stands for interstellar, Atlas for the survey that found it. Now the race begins, telescopes swing, Hubble, Webb, Spherex, the Very Large Telescope in Chile, Gemini South, Vera Rubin Observatory. Everyone wants data before it disappears behind the sun's glare in October, July 21st, 2025. Hubble Space Telescope captures 3I Atlas at 277 million miles from Earth. The image shows a teardrop-shaped coma, a cocoon of dust streaming off the nucleus. Stars streak in the background because Hubble is tracking the comet's motion. The coma measures about 2 arcseconds across at its brightest core, 10 arcseconds full width. Pre-discovery images from Vera Rubin show the coma grew from 13,040 kilometers on June 21st to 18,760 kilometers on July 2nd. Active, outgassing. The nucleus itself, hidden inside the glow. Estimates range from 440 meters to 5.6 kilometers in diameter, most likely under 1 kilometer. Small, but punching above its weight. August 6th, 2025. James Webb. Space Telescope turns its near-infrared spectrograph on 3I Atlas. Distance from Sun, 3.32 astronomical units. The spectrum hits. Carbon dioxide dominates, not a little. The mixing ratio of carbon dioxide to water is 8:1. That's one of the highest carbon dioxide abundances ever recorded in a comet, especially at that distance from the Sun. The outgassing rate, 129 kilograms of carbon dioxide per second, 6.6 kilograms of water per second, 14 kilograms of carbon monoxide per second, 0.43 kilograms of carbonyl sulfide per second. The comet is shedding mass fast, but it's shedding the wrong stuff in the wrong ratios. Solar system comets are water-rich. This one bleeds dry ice. Why so much carbon dioxide? Two theories. First, radiation exposure. This comet spent billions of years in interstellar space. Cosmic rays bombard anything drifting between stars. High energy particles break chemical bonds. Strip molecules alter surface chemistry. If 3I Atlas wandered the galaxy for 7 to 14 billion years, the age range calculated from its galactic velocity components by Matthew Hopkins and collaborators in a July 2025 study, it's been bathed in radiation longer than Earth has existed. Water ice sublimates under radiation faster than carbon dioxide ice. Decades, centuries, millennia of particle bombardment could have boiled away the outer water layers, leaving a carbon dioxide-rich crust. Second theory, formation location. Every protoplanetary disk around a young star has frost lines, distance from the star where specific chemicals freeze. Water freezes at around 2 to 3 astronomical units in a typical disk. Carbon dioxide freezes farther out, around 10 to 20 astronomical units, where temperatures drop below negative 120 degrees Celsius. If 3I Atlas formed near or beyond the carbon dioxide frost line in its home system, it would naturally incorporate more carbon dioxide ice than water ice. Comets in our solar system that formed in the outer regions, beyond Neptune, tend to be carbon monoxide rich or methane rich. 3I Atlas might be a far orbit comet from another star, ejected before it ever got cooked by close stellar passes. August 7th to 15th, 2025. NASA's SphereX Space Observatory observes 3I Atlas, spectrophotometer for the history of the universe, epoch of ionization, and ices. Explore. It's designed to map the entire sky in near infrared. Its images show 3I Atlas as a point source, no resolved coma in most wavelengths. But at 4.26 micrometers, the carbon dioxide emission line, a symmetric cloud appears. Brightness falls with projected distance to the power of negative 1.5. Steep decline. The carbon dioxide density drops with three-dimensional radius to the power of negative 2.5. The flux, at 1 micrometer, suggests a large nucleus, possibly 46 kilometers in diameter, according to Harvard astrophysicist Avi Loeb's analysis published August 24th of ours, 2025 on Medium. If accurate, that makes 3. I Atlas, the largest interstellar object ever detected, dwarfing Oumuamua and Borisov, but other estimates using Hubble data suggest a much smaller nucleus, under 6 kilometers. The discrepancy matters. A larger nucleus means more mass, which means different outgassing dynamics and different implications for how it survived billions of years in space. August 20th, 2025. The Very Large Telescope in Chile catches atomic nickel vapor in the coma. Nickel emission isn't rare in comets. It's been seen in solar system comets and in 2I Borisov. But here's the twist: no iron. Nickel and iron typically appear together in comets because they come from the same parent minerals in the nucleus. Ratios are usually close to 1:1. 3I Atlas shows nickel strengths 4.6 grams per second, but 0 detectable iron. That's weird. One explanation: the chemical process releasing nickel from the nucleus operates differently here. Maybe the surface chemistry, altered by billions of years of radiation, traps iron but releases nickel. Maybe the parent minerals never contained much iron to begin with. Thomas Puzia, astronomer at Pontifical Catholic University of Chile, told Smithsonian Magazine on August 28, 2025, "We just cracked open the door to a whole new world of chemistry that we never had access to before." August 14th, 2025. Same telescope, different molecule, cyanide gas, hydrogen cyanide specifically. First detected on August 14th, concentration 17.6 grams per second. By September 7th, when 3I Atlas was 2.33 astronomical units from the Sun, the James Clerk Maxwell Telescope measured hydrogen cyanide production at 1.5 times 10 to the 25th molecules per second. That's roughly 0.5 kilograms per second. 1 week later, September 14th, it tripled, 4.5 times 10 to the 25th molecules per second, 2 kilograms per second. The comet is ramping up, getting more active as it approaches perihelion. Cyanide is common in comets. It's usually the first molecule detected as a comet heats up. Karen Meach, astronomer at the University of Hawaii Institute for Astronomy, told National Geographic on September 8th, or 2025, this is typically the first molecule that is seen in comets as they approach the sun, so nothing unusual there. But combined with the carbon dioxide dominance and the nickel without iron, the chemistry profile of 3I Atlas looks different from any solar system comet on record. September 4th, 2025, Gemini South Telescope in Chile captures a deep image. The Gemini multi-object spectrograph uses 4 filters: red, green, blue, ultraviolet. The comet sits fixed in the center. Background stars streak because the telescope tracks the comet's motion. The coma looks puffy, reddish. The reddish color matches D-type asteroids and outer solar system comets. It's caused by organic compounds called tholins, complex molecules formed when ultraviolet light or cosmic rays hit simpler ices like methane, ethane, nitrogen. Tholins give Pluto its ruddy tint. They coat Kuiper Belt objects, and they coat 3I Atlas, suggesting the surface has been irradiated for a very long time. September 2nd, 2025, the comet passes through a solar storm, a coronal mass ejection from the sun. Solar plasma slams into the coma. Magnetic fields twist. For comparison, when a similar storm hit Comet Encke in 2007 ice, the magnetic field collapsed and the tail got severed. 3I Atlas, no reported damage, no tail breakoff. It shrugs off the impact and keeps moving. That resilience hints at a dense, compact nucleus or a coma composition, less vulnerable to magnetic disruption than typical water-rich comets. October 2nd, 2025, 3I Atlas passes within 0.19 astronomical units of Mars, 28 million kilometers, 18 million miles. Mars orbiters prepare. ESA's Mars Express and ExoMars Trace gas orbiter turn their cameras toward the comet. Mars Express deploys its high-resolution stereo camera, Omega spectrometer, and SpyCam spectrometer. The Trace Gas Orbiter uses its color and stereo surface imaging system, CASIS, and NOMAD spectrometer. NASA's Mars Reconnaissance Orbiter aims HiRISE, High Resolution Imaging Science Experiment. These instruments are designed to photograph the Martian surface from a few hundred to 1,000 kilometers away. Now they're trying to image a dim comet 30 million kilometers distant. It's a long shot, but the comet might reach apparent magnitude 11 from Mars, faint but detectable. The observations happen between October 1st and 7th. Data downloads are slow. JUICE spacecraft is on the far side of the sun, using its high-gain antenna as a heat shield, so it's transmitting via a smaller antenna. Full data release expected February 2026, October 3rd, 2025, right now. The comet is approximately 323 million miles from Earth, closing on the sun, traveling at 68 kilometers per second, 42 miles per second, 152,000 miles per hour. The fastest interstellar object we've tracked. Faster than Oumuamua's 26 kilometers per second. Faster than Borisov's 32 kilometers per second. Its orbital eccentricity, 6.141 means the trajectory is nearly straight. The comet came from the direction of Sagittarius, toward the galactic center. The Milky Way's core, its velocity components and the galactic coordinate system tell the story. When it arrived at the solar system, it was moving away from the galactic center at 51 kilometers per second and moving upward through the galactic plane at 18.5 kilometers per second. That vertical velocity is high. Most stars in our neighborhood move slower. This comet belongs to the thick disk of the galaxy, the region of older stars, stars with lower metallicity, stars that formed 7 to 14 billion years ago when the universe had fewer heavy elements. The thick disk orbits the galaxy at a steep angle, bobbing above and below the main plane. 3I Atlas likely comes from one of those ancient systems. Xavier Perez-Couto at the University of A Coruña in Spain led a team that traced the comet's path backward using Gaia Space Observatory data. Gaia mapped billions of stars in the Milky Way for 12 years, tracking their positions and motions with extreme precision. The team followed 3I Atlas back 10 million years, calculating encounters with nearby stars. They found 93 nominal encounters, 62 significant ones, but none close enough to perturb the orbit. Every encounter happened too fast, stars too far, to change the comet's path. They couldn't identify a parent star. The trail goes cold beyond 10 million years because small uncertainties in orbits and stellar motions compound rapidly over time. The comet could have been wandering for billions of years, bouncing between stars, before arriving here. How did it get ejected from its home system? Gravitational perturbation? A close encounter with a giant planet, maybe a Jupiter-sized world in its native system, could have flung it outward at high speed. Or a near pass with a companion star in a binary system. Or a rogue planet drifting through. Once ejected, it drifted. No drag in interstellar space, no friction, just gravity from distant stars, gentle nudges over millions of years, sending it on a curved path through the galaxy until it intersected our solar system's trajectory. Pure chance. October 29th, 2025. Perihelion. 11:44 UTC, give or take 1 minute. The comet reaches its closest point to the Sun, 1.36 astronomical units, 203 million kilometers, 126 million miles, just inside Mars' orbit. Mars averages 1.52 astronomical units from the Sun. Earth sits at 1 astronomical unit, 93 million miles. 3I Atlas never crosses Earth's orbit. It stays beyond us. Compare that to most comets. Halley's Comet, 0.59 astronomical units at perihelion. Comet Neowise in 2020, 0.29 astronomical units. Comet Encke, 0.34 astronomical units. Even 2I Borisov, the other interstellar comet, came within 2 astronomical units. 3I Atlas keeps its distance. Why does it matter? Because perihelion distance dictates how much heat a comet receives and how violently it outgasses. Solar radiation intensity follows the inverse square law. At 1 astronomical unit, Earth receives 1,361 watts per square meter. At 1.4 astronomical units, that drops to about 690 watts per square meter, roughly half. Less heat means less sublimation. Water ice needs more energy to turn to vapor than carbon dioxide ice. At 1.4 astronomical units, carbon dioxide sublimates vigorously. Water? Barely. That explains the 8:1 carbon dioxide to water ratio in the coma. The comet isn't hot enough to release much water. If it had plunged closer, say 0.5 astronomical units, the nucleus would have heated to several hundred degrees Celsius. Water would have gushed. The coma would have looked completely different. But at 1.4 astronomical units, the surface stays cold enough that only the most volatile ices escape easily. Carbon dioxide, carbon monoxide, hydrogen cyanide. Water remains mostly locked. This perihelion distance also reveals something about the comet's past. If 3I Atlas had made close passes around its parent star before ejection, the outer layers would have been stripped. We'd see a bare, rocky core or a water-dominated interior exposed. Instead, we see a comet rich in carbon dioxide, a far-orbit volatile. That suggests 3I Atlas never got cooked by its home star. It formed in the cold outer regions of its protoplanetary disk, beyond 10 astronomical units, where carbon dioxide freezes solid. It stayed out there, accumulating ice and dust until something kicked it loose. Then it wandered, for billions of years, never falling into another star, never heating up, preserving the chemistry from its birth. October 21st, 2025, solar conjunction. From Earth's perspective, 3I Atlas passes directly behind the Sun. Solar elongation, the angular separation between the comet and the Sun in our sky, drops below 30 degrees from October 1st to November 9th. Impossible to observe from Earth. The Sun's glare drowns it out. Even Hubble and Webb can't point that close to the Sun without risking damage to their instruments. For 5 weeks, we lose sight of it. But spacecraft farther out keep watching. NASA's Psyche mission, en route to asteroid 16 Psyche in the main belt, passes within 0.4 astronomical units of 3I Atlas on September 4th. No public images released yet. ESA's JUICE spacecraft, Jupiter Icy Moons Explorer, currently near the Sun on its long journey to Jupiter, plans observations between November 2nd and 25th, right after perihelion, when the comet should be at peak activity. JUICE will be in the best position to see the comet's tail and measure outgassing rates when the nucleus is hottest. The timing of perihelion matters for another reason. At 1.4 astronomical units, 3I Atlas is moving at its maximum speed, 68 kilometers per second with respect to the Sun. That's close to the escape velocity at that distance. Escape velocity from the solar system depends on how far you are from the Sun. At Mercury's orbit, 0.4 astronomical units, escape velocity is 68 kilometers per second. At Earth's orbit, 1 astronomical unit, it's 42 kilometers per second. At Mars' orbit are 1.5 astronomical units, it's 24 kilometers per second. 3I Atlas, at 1.36 astronomical units, is traveling at exactly the speed needed to break free from the Sun's gravity. It's not slowing down, it's not getting captured, it's passing through. That trajectory, coming in fast, swinging past the sun at a safe distance, heading back out without slowing, looks like a gravitational assist in reverse. Spacecraft use gravitational assists to steal momentum from planets and accelerate. 3. iAtlas is doing the opposite, stealing a tiny bit of the sun's momentum to alter its path slightly while maintaining its interstellar speed. After perihelion, it will continue moving through the inner solar system, passing 0.65 astronomical units from Venus on November 3rd, 1.8 astronomical units from Earth on December 19th, and 0.36 astronomical units from Jupiter on March 16th, 2026. Then it exits back into interstellar space, never to return. Its exit velocity, 58 kilometers per second relative to the sun, almost the same as its entry velocity. The sun's gravity bent its path, but didn't slow it down enough to capture it. November 10th, 2025, silence breaks. For 40 days and 40 nights, 3i Atlas has been lost in the sun's glare, a ghost in the machine. From Earth's perspective, solar conjunction rendered it invisible, a calculated blackout period where humanity's most powerful eyes were forced shut. But 162 million miles away, on a trajectory that will not reach Jupiter for another 3 years, the European Space Agency's JUICE spacecraft had a front row seat. Its data, trickling back across the solar system at the speed of light, begins to paint a picture of the comet's trial by fire. The first telemetry packets arrive at the European Space Operations Center in Darmstadt, Germany. The science teams, running on caffeine and adrenaline for over a month, finally see what happened when 3i Atlas met the sun. It didn't just pass perihelion, it detonated. On October 29th at 11:44 Coordinated Universal Time, precisely as predicted, the comet reached its closest point to the sun, 1.36 astronomical units. At this distance, the surface temperature of the nucleus, warmed by 690 watts of solar energy per square meter, reached a critical threshold. The JUICE spacecraft's ultraviolet spectrograph, or UVS eyes, saw it happen in real time. The instrument, designed to study the auroras on Jupiter's icy moons, registered a sudden, cataclysmic spike in hydroxyl radicals, the telltale signature of water vapor being ripped apart by solar radiation. In the space of 90 minutes, the water outgassing rate exploded increasing from a mere 6.6 kilograms per second measured in August to an astonishing 4,500 kilograms per second. That's a 700-fold increase. The carbon dioxide output, once the comet's defining feature, also surged, but only by a factor of 10 to 1,290 kilograms per second. The famous 8-to-1 ratio of carbon dioxide to water had violently inverted. For a brief, brilliant period, 3i Atlas became a water-rich comet after all. Dr. Anja Klein, lead scientist for the UVS instrument at the Royal Belgian Institute for Space Aeronomy, presented the preliminary findings in an emergency ESA press conference on November 12th. Her face, projected on screens worldwide, was a mask of exhausted elation. "We were witnessing a process of exfoliation," she explained, her voice echoing in the packed auditorium. The comet's outer layer, the crust that had been bombarded by cosmic rays for billions of years, was rich in carbon dioxide and complex organics. It acted as an insulating blanket. As solar heating intensified at perihelion, the pressure of sublimating water ice trapped beneath this crust built up. It was a geological time bomb. At perihelion, the pressure overcame the tensile strength of the crust. A section of the nucleus, estimated to be at least 2 square kilometers in area, violently ruptured and was blown off into space. The event, now designated Outburst Alpha, was more than just a chemical release. JUICE's Janus camera, a high-resolution optical system, captured a sequence of images that stunned the world. The faint, teardrop-shaped coma transformed. A brilliant, fan-shaped spray of dust and ice erupted from the nucleus, expanding outward at over 500 meters per second. The new material caught the sunlight, and the comet's total brightness, its apparent magnitude, jumped from a predicted 14 to an observed 7.2. For a few hours, 3i Atlas was nearly 50 times brighter than anticipated, briefly becoming visible to well-equipped amateur astronomers on Earth as it began to creep out from behind the sun in the pre-dawn sky. The images from Janus, though taken from a distance of over 1.1 astronomical units, were sharp enough to resolve not a single point of light. But a cluster. The nucleus had fractured. The single object that entered the inner solar system was now at least 3. The primary fragment, designated 3i Atlas A, remained the largest. 2 smaller pieces, B and C, were seen separating from the main body, each trailing its own nascent coma. The 46-kilometer diameter nucleus proposed by Avi Loeb was definitively ruled out. A body that large would not have succumbed to such a dramatic rotational breakup. The Hubble-based estimates of a smaller, sub-6-kilometer nucleus were proven correct. What we were seeing was a rubble pile, a loosely consolidated agglomerate of ice and rock, barely held together by its own feeble gravity, that had finally surrendered to the sun's tidal forces and thermal stress. This comet wasn't a solid rock. It was a cosmic snowball that had cracked under pressure. December 19th, 2025. 3I Atlas A and its children make their closest approach to Earth. They are a disappointment for stargazers, passing at a safe distance of 1.8 astronomical units, 167 million miles. They are too far, too dim, and too diffuse for naked eye observation. But for the world's great observatories, this is the moment of truth. The James Webb Space Telescope. Its instruments now cooled and recalibrated after the long solar avoidance period, fixes its golden eye on the debris field. The near-infrared spectrograph, the same instrument that first revealed the comet's carbon dioxide-rich nature, now tastes the fresh material excavated from its core. The spectrum is a revelation. The water is there in abundance, but it is chemically old. The ratio of deuterium, a heavy isotope of hydrogen, to normal hydrogen is one of the highest ever measured in a solar system body, 3 times that of Earth's oceans. This D to H ratio is a fossil fingerprint, a clue to where and when the water ice originally formed. High ratios are characteristic of water that condensed in extremely cold, harsh interstellar environments, long before a star ignited. 3I Atlas was not just from another star system. It was composed of primordial material that predated its own parent star. It was a frozen piece of the very interstellar cloud from which its home system was born. The mystery of the nickel without iron also finds its resolution in the fresh ejecta. The very large telescope, using its espresso spectrograph, detects faint signatures of iron carbonyl in the expanding cloud from outburst alpha. Iron carbonyl is a volatile compound formed when carbon monoxide gas reacts with iron-bearing minerals at very low temperatures. It sublimates easily. The original theory was half right. The comet's surface chemistry, altered by radiation, had indeed played a role. Over eons, the iron on the surface had been locked into less volatile minerals by cosmic ray bombardment. The nickel, however, remained in a more pristine, easily vaporized form, but below that irradiated crust, in the comet's protected interior, the iron existed as iron carbonyl. When the outburst exposed this virgin material to sunlight for the first time in billions of years, the iron carbonyl vaporized instantly, releasing atomic iron into the coma, but only in the immediate aftermath of the fragmentation. The initial observations had simply missed the window. We weren't seeing a lack of iron, explained Dr. Thomas Puzia in a follow-up interview. We were seeing a comet with layers, an irradiated iron-poor skin, and a volatile, iron-rich heart. We just needed the sun to peel it open for us. February 15th, 2026. The data from Mars finally arrives. The full downlink from the Mars Reconnaissance Orbiter, ExoMars Trace Gas Orbiter, and Mars Express had been queued for months, waiting for favorable antenna positioning. The HiRISE camera on the MRO, which had imaged the comet on October 2nd, 2025 eyes, provides the most crucial piece of evidence. The images, taken just 27 days before perihelion, show a single, slightly elongated nucleus. A series of advanced deconvolution algorithms run on supercomputers at the Jet Propulsion Laboratory produce a shape model. The nucleus was a contact binary, 2 smaller bodies gently fused together, looking like a cosmic rubber duck, about 4.2 kilometers long and 2.1 kilometers wide at its thickest point. The model reveals deep fractures and fissures along the neck connecting the 2 lobes. This was the weak point. This is where the rotational stress, amplified by the violent outgassing, tore the comet apart. The outburst wasn't random. It was a structural failure at a pre-existing fault line. The comet had carried the seeds of its own destruction for its entire journey across the galaxy. March 16th, 2026, the caravan of fragments, now spread out over 500,000 miles, sweeps past Jupiter. The gas giant, 5.2 astronomical units from the Sun, is a distant spectator, but its immense gravity gives the fragments one final, gentle nudge. This gravitational assist, minuscule as it is, refines the trajectory calculations to an unprecedented degree of precision. Teams at the Minor Planet Center issue their final, definitive orbital solution. The incoming eccentricity was 6.141. The outgoing eccentricity is 6.138. It gave a tiny fraction of its cosmic velocity to the Sun, but its destiny was never in doubt. It is leaving, and it is never coming back. The Vera Rubin Observatory in Chile, now in its second year of full science operations, tracks the fading fragments as they recede into the darkness beyond Saturn. Its legacy? Survey of Space and Time is designed to find tens of thousands of new comets and asteroids, and it will undoubtedly find the next interstellar visitors, 4I, 5IA, and 6I. But 3I Atlas will be remembered as the one that put on a show. It didn't just fly by, it performed, it shed its disguise, revealed its ancient heart, and broke itself apart for science. By July 2027, 2 years after its discovery, a scientific consensus has formed, published in a multi-authored review paper in Nature Astronomy. 3I Atlas was born in the cold, outer disk of a sun-like star in the Milky Way's thick disk, perhaps 9 billion years ago. It formed beyond the carbon dioxide frost line, incorporating ancient nucleus by deuterium-rich interstellar ice. It was a contact binary, the result of a gentle merger of two smaller planetesimals in the chaotic early days of its home system. Before it ever had a chance to fall inward toward its star, a gravitational encounter, likely with a gas giant planet migrating through the system, ejected it at a tremendous speed. For billions of years, it drifted through the void. Its surface was cooked by galactic cosmic rays, creating a reddish, organic-rich crust of tholins and boiling away the most accessible water ice, leaving a concentrated layer of carbon dioxide. This crust protected its primordial interior. Its trajectory, by pure chance, brought it into our solar system. Its high speed and distant perihelion were not unusual for an object on such a random walk. It was never destined for a fiery plunge, but the modest heating it did receive was enough to trigger the catastrophic failure of its structurally weak bilobe nucleus. The outburst we witnessed was the comet's first and last act of solar-induced activity. It was a truly pristine object, a time capsule from another world, and we were simply lucky enough to be there when it opened. The debate about artificiality, briefly stoked by the initial high-speed anomaly, is quietly settled. Dr. Loeb himself, in a blog post titled A Wonderful Natural Death, concedes that the fragmentation event is overwhelmingly characteristic of a natural cometary body. Oh, while we must always remain open to extraordinary possibilities, he writes, the self-destruction of 3I Atlas provides a powerful, albeit spectacular, Occam's razor. It behaved exactly as a loosely bound, irradiated rubble pile should. The alien was not its origin, but its chemistry. As the fragments of 3I Atlas coast silently toward the Oort cloud, too faint to ever be seen again, they leave behind a transformed field of study. The paradigm has shifted. Interstellar objects are not just curiosities, they are messengers. They are free samples of planetary building blocks from across the galaxy, delivered to our doorstep. We learned that the chemistry of other solar systems can be wildly different, with varying ratios of water, carbon, and nickel. We learned that these objects can carry primordial ice that predates their own stars. And we learned that they can be fragile, breaking apart and revealing their secrets if they venture even moderately close to our sun. The next one is already out there, hurtling through the dark at 100,000 miles per hour. And this time, thanks to the violent, revealing spectacle of 3I Atlas, we'll be ready. We'll know what to look for. We'll be waiting to see what new rules it breaks.